Before we get into the topic of Maclaurin and Taylor polynomials, I'd like to do a brief introduction. I'm going to show you a familiar graph, and I want you to guess what the graph of this is. Okay. Let me show you. Let me graph it out first. Okay, so just take a guess and tell me what you think this is. All right, so most of you probably are thinking that it's just a straight line, maybe y is equal to x. All right, now I'm going to show you the same graph, and it's going to be a different window. All right, would you like to change your mind? Okay, so compare this first one, which looks like a linear, and then compare it to the next one. Now it's kind of looking like it's a cubic graph. All right, let me take the first one away, and here was the second one. And now I'm going to show you a third graph, and that's this. Now what do you think it is? All right, so now you probably will guess that this is a sine graph. So depending on the window that you're in, it could be very deceptive what type of a graph it is. Because if you go into the graph and look at it in a very magnified way, so if I were to look at just this middle portion right here, you could see that this is a straight line. So my window is very much magnetized in this region. And then if I make the window a little bit larger, which I did with the second graph, it looks like it's a cubic. But in fact, this is a sine graph. All right, so what we have learned from back in section, I think it was chapter 3, is that you can have a linear approximation at any point on any kind of graph. All right, so I'm going to give you an example. So suppose that you have y is equal to sine of x, and if you wanted to find the linear approximation, and let's say that it's going to be at x is equal to 0. All right, so if you remember the procedure on this, I want to get it of the form y minus y1 is equal to m quantity x minus x1. So I need to first of all find my slope, which means that I have to take the derivative of y. So y prime is equal to cosine of x. And then I'll figure out what the slope is at 0. So y prime of 0 is equal to the cosine of 0, which is equal to 1. So my slope is equal to 1. And then I am going to figure out the y value. So I have y of 0 is equal to sine of 0. And sine of 0 is 0. So I have the point at y of 0 is equal to 0. All right, so now I'm able to write out my equation. So it'll be y minus 0 is equal to m is 1 times x minus 0. So I get an answer of y is equal to x. So this is what we called as the linear approximation at x is equal to 0. Right, so let me go back to the graph that I had originally shown you on this. So for this one right here, you can see that at x is equal to 0, this is actually going to be a very good approximation. However, if you get farther away from it, like at pi over 2 right here, or pi, it's actually not a very good estimation at all. In fact, it's a horrible estimation. And so what the Maclaurin and Taylor polynomial does is it makes it so that it's an extension of linear approximation, right? And then we're able to figure out certain approximations. So for example, if you have a function like g of x is equal to the cosine of x, for certain values, especially the ones that are nice on the unit circle, you can get the value. But what if you were asked, what is the cosine of 8? Right? That is not an easy one to calculate. How about this one? If you have an h of x is equal to e to the x, if x is 1 or 0 or 2, those are nice values that you could actually estimate. But what if you were asked about e to the 7.3? Okay, that would also be very difficult to estimate. And then one last one, if you had k of x is equal to the square root of x, If they were perfect squares, for example, square root of 1, square root of 4, square root of 9, those would come out to be nice values. But what about a square root of 11? Right? That would be difficult to calculate. So, in a nutshell, what Taylor polynomial and Maclaurin polynomial is, it's a polynomial function, and polynomials are always very nice to work with because the derivatives are easy, the integrals are fairly easy, and you can also plug in values, substitute in values, and they come out easy to calculate. And so Taylor polynomials and Maclaurin polynomials are polynomial functions that we use in place of hard functions. So we consider these as difficult functions. And so you're going to be using that in order to estimate difficult numbers. So that is what we are going to be looking at in our class notes with the Maclaurin and Taylor polynomials.